Okay, we're recording.
Okay. So I'm trying to continue from this, basically the same ideas that we were talking about last time, which, how do we try to summarize it? I'm trying to understand torsors over number fields and in a sort of very Tanakian way. Although I'm not sure how much we'll really see the Tanakian focus today. I'm really aiming for that. But I'm sort of expecting I'm going to get into a lot of concrete examples today, which may be sort of, some of it is just like raw material for trying to impose a Tanakian viewpoint on this. But anyway, I'm still trying to take a Tanakian viewpoint on torsors over number fields. And yeah, what do we mean by Tanakian? I mean, sometimes people mean different things by Tanakian. In this case, I mean something like that. We're trying to understand these torsors, which are conceptually something like principal fiber bundles, but perhaps in a very abstract context compared to a more traditional topological context. That we're thinking of these principal fiber bundles or torsors, we're thinking of them in this Tanakian functorial way. Right. So, you know, to a principal fiber bundle, we have this idea of the associated vector bundles coming from group representations, representations of the structure group, whatever you call it. And that association functor, associated vector bundle functor, is our conceptual picture of what the torsor is, what this principal fiber bundle is. And that's the very rough idea of the Tanakian viewpoint. But okay.
Can I interrupt about the Tanakian viewpoint? So whenever I hear Tanakian viewpoint, I think of something more like this, like you've got the category of representations of the group, and then it's forgetful functor down to vector spaces. And then from that, you reconstruct the group. So you're doing something.
Right, you're doing Tanakian, you're talking about Tanakian reconstruction of groups. And I'm sort of emphasizing more the idea of Tanakian reconstruction of torsors of groups. You know, so maybe this is sort of like at a lower level than the Tanakian reconstruction of the group or something like that. But it's all fitting together.
Yeah, it's interesting. I've never heard of this thing you're talking about as being Tanakian, but anyway, it involves the representation category rather than the group itself. So in that way, it's yes, that's right. That's right. So it's adapting the torsors or the principal fiber bundles to the Tanakian picture, where you think in terms of the representation category as the manifestation of the group. Mm-hmm. So one of our plans here is that, you know, we were able to understand, for example, Z mod 2 torsors in a pretty straightforward way due to the fact that how do people say it, that Z mod 2 splits over the rationals, that its representation theory is already all there. It's all one-dimensional representations, one-dimensional irreducible representations over the rationals, even before you get to the complex numbers or anything like that. Whereas in contrast, Z mod 3 is already presenting us some new phenomena here, due to the fact that Z mod 3 does not split over the rationals. For some reason, I'm motivated to digress more. So, you know, the symmetric groups all split over the rationals. Now, all of a sudden, you're making me wonder, like, which groups split over the rationals? Because you might think, like, oh, it's only Z mod 2, because every higher cyclic group has these roots of unity that aren't in the rationals. And so you might say, well, if Z mod 3 doesn't split, then how in the world would S3 split? But somehow
it's weird. Yeah, it's weird. I mean, but I mean, there are all sorts of things to say about that. None of none of which I'm intelligent enough to say at the moment, or very few of which but one thing, one vague response I have to that is that, there are these families. What am I trying to say? I can't remember the names of any of these things, but I mean, if you take a group like an algebraic group, let's say like GLN, then it has this whole family of manifestations over finite fields. So you can talk about GLN over a finite field.
Mm-hmm.
And so you're talking about GLN comma F sub Q. Somehow that letter Q there is mystically important. It's related to Q polynomials and stuff like that there. And furthermore, that opens up the possibility of thinking about the case Q equals 1. There are cases where Q is the size of a field, but then there's this mysterious pretend field where Q is equal to 1. And people try to figure out what they mean by that, or they try to work with it without figuring out what they mean by it. And so how does it work? I always have trouble with these like fence post mistakes, but GLN comma F sub Q, in some sense, if you set Q equals to 1, one interpretation of that is it has to do with N bang, the symmetric group on N letters or something like that.
Yeah,
something like that.
Yeah, that's right. No fence post error there. Yeah.
Yeah.
You've got the coordinate axes left is how I think of it.
Yeah. So what I was attempting to say here was that it sort of seems like in these examples, when Q equals 1, we have a lot better chance of getting the thing to split over the rationals. And then as Q becomes, some more familiar prime power, then there's a much more of a tendency for not to split over the rationals. And this should be fun, right? I mean, it could be.
Yeah, it's sort of like only bad at that particular prime that Q is the power of, I think. So like probably like if you fix the rationals a little bit at the prime P, maybe then it would split.
Well, or something like that. It might also, right, have to do with, what am I trying to say? I mean, there are a lot of primes that are not equal to Q that divide the order of GL1 comma Q, for example. Is that relevant here? I'm not sure.
Oh, yeah, I guess you're right. Yeah, I guess you're right. So Moshka's theorem says that. What is Moshka? I don't know for sure if that means it doesn't split over those. Yeah. Moshka's theorem says it does.
All right, I'll have to learn about that, but I don't know about
I think Moshka's theorem says that the field, that a group would split if it's over F P, to be safe, if P doesn't divide the order of the group. Did I say that right? Finite group splits over some prime power field if that prime doesn't divide the order of the group, which is sort of what you're alluding to.
Oh, yeah, right. Something like that. Yeah, something like that may be true. But
yeah, so my first statement was probably just balloon. Yeah.
Okay, but so this was a slight attempt on my part to respond to your question. I mean, I'm not suggesting any source of things that do split over the rationals, but I'm also suggesting that it's very interesting when they don't split over the rationals. And
right. Well, that's why we're going straight to Zima 3s. Okay.
Yes, but also and to put these in these families and compare the different members of the family and how they're how they maybe have related representation theory, but Right, there's all the stuff about cuspidal representation, stuff like that. Anyway, that was yeah. I'm not even sure what I'm saying, but that was some attempt to respond to what you brought up. Now I have to try to remember where we were before we went into that little digression. So yeah, well, right. We were just mentioning that we're in terms of concrete examples, we're really interested in Z mod 2 torsors as a case that we've already think we understand a lot, but then as a new case, we're really interested in Z mod 3 torsors. And so we're trying to do for Z mod 3 a lot of things that we already know how to do for Z mod 2. And that's kind of where we're exploring it. And so as part of that plan, as part of that theme, that plan, so I really want to look at, well, so there's this example that I've often looked at, which is very related to Z mod 2. And that example is the 20th cyclotomic field. And so what is it called? The Euler totient of 20. It's 8. It's, you know, it's basically the Euler totient is the decategorification of the general linear group in one dimension, right? It's the decategorification, in some naive sense, it's the decategorification. It's just the size of the multiplicative group.
Yep.
Of
luckily, I have the enormous chart that you repeatedly draw.
aha, okay. So
I mean, you have it too somewhere.
yes.
I could I forget. It's February 16th. So for viewers of this video, they can look at the February 16th video and see an exhaustive working out of this 8-element group that you're alluding to. And all sorts of
yeah, so right. I mean, let's write down
like all
its what it is.
Subgroups.
It's like GL1, comma Z mod 20, right? And it's this 8-element group that we can understand a lot by Chinese remainder theorem type thinking.
Is it just a coincidence that it has 8 subgroups?
I think that is, yes. And I wouldn't have known that. I wouldn't, right. It seems bad that we.
It's like some new version of Fourier duality that they never told me about.
Yeah, I mean, it seems like I never realized that was just a coincidence, I don't think, until I started thinking about the 3 case. But let's see. So what is going on here? We have the prime 2, but it's to the 2nd power, and we have the prime 5. And so the multiplicative group for Z mod 5 is like 1, 2, 4. Yeah, that's the. I wrote it in the order of the powers of 2 mod 5, and the multiplicative group of Z mod 4 is just the 2 elements 1 and 3, and then by the Chinese remainder theorem, you figure out what this is. I guess it's like what, 1, 11, maybe let's see. Maybe
you were so
7,
good at it last time.
Yeah, 7,
I
17.
can look it up if you want.
Well, let's see. Okay, this must be like 9 and 19, right?
Yeah.
I mean, anybody can check and see if I made mistakes, but yeah, I was just sort of trying to remember it by using little clues that I should remember. So, yeah, and right, and then there's, as you say, there's these 8 subgroups, and it looks something like what? Well, so yeah, there's 8 I'm trying to draw these 8 subgroups arranged in this hierarchy. And you know, this is sort of the Galois correspondence for the subfields of the 20th cyclotomic field. And what does it look like? Something like that. And okay, so it's the Galois correspondence. So it's got upside down. So it's got the smallest group at the top. It's got the biggest group at the bottom. Let's see. Well, et cetera, et cetera, et cetera. But we're going to try and do something like this for 3. Because we're really, well, so, right, I mean, is it clear that, right, in this picture, that somehow right at this level is where there's a lot of Z mod 2 torsors living. I mean, there's a lot of quadratic extensions. Well, there's 3 quadratic extensions of the rationals living right at that level. And you can sort of reinterpret those quadratic extensions as being Z mod 2 torsors. And we're going to try to do something like that for Z mod 3, but you know, but we have to think a little bit about it, about which cyclotomic field to use, because, right, part of the point is that if you just happen to pick the 20th cyclotomic field, then the Euler totient happens to be this power of 2. And somehow that's very helpful for getting these quadratic things. But so I think, right, so to get some stuff going for cubic extensions of the rationals, and abelian cubic extensions of the rationals, that we can reinterpret as Z mod 3 torsors. I think a good number to pick is the 63rd cyclotomic field. So you know, 63 is equal to what? 3 squared times 7, does that seem right? And so we're going to have, you know, the Chinese remainder theorem going on here, separating the primes 3 and 7. So let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. All right. Again, it would be better if I had prepared all these drawings ahead of time, but I didn't manage to do any of that today.
Is there some reason why you picked such a big number as 7?
I guess yes.
I assume so.
It's
Not
because
just masochism.
well, yes, again, the whole idea, you know, so you have to think about it. You have to sort of plot it out that we're trying to get as rich a supply of cubic, abelian cubic extensions of rationals as we can. Cubic extensions of the rationals that live inside the cyclotomic numbers, which makes them abelian. So let's see, we're gonna have 3 squared. So is that right? So it just happens that both of these numbers, 9 and 7, they both have the same Euler totient, which is 6. And somehow that 6, you know, is very helpful in terms of getting cubic stuff going on. So we're gonna have what? So I think it's like 1, 3. Okay, this is the powers of 3 mod 7, because 3 is, I think, a whatever you call it, a primitive element or something, a generator of the multiplicative group. mod 7. So I think it's 1, 3, and then 2. And then 2 times 3 is 6. 6 times 3 is 4. 4 times 3 is 5. And yeah, that's it. 5 times 3 is back to 1. And over 9, 2 is a generator. And so we just have the powers of 2. So it goes 1, 2, sorry. 1, 2, 4, 8, and I think 7 and 5, like that. And at some, yeah. Somewhere in my notebook, I have a complete filling in of the Chinese remainder theorem for this one, but I don't have it right at my fingertips at the moment. So maybe we won't really, I don't know how much we'll need that. If we really do some of these concrete experiments and calculations, then we may actually need some of that Chinese remainder data. So this is what? This is Z mod 6 cross Z mod 6. It's a 36 element abelian Galois group. And so what do the cubic extensions correspond to here in the Galois correspondence? So they correspond to, the Galois correspondence is upside down, so these should be the subgroups of index 3. And okay, but now, okay, so 6, right, it's very helpful that 6, both of these 6s are divisible by 3. That's very helpful. But on the other hand, you might think that the factors of 2 here are just an annoyance, but actually they're not completely an annoyance. The factor of 2 in the 3 dimension is actually helpful because that has something to do with the Eisenstein integers, which is the primitive cube roots of unity, but it's a quadratic extension of the rationals, right? So there's some funny interplay, right, between quadratic and cubic stuff here, because right, the Eisenstein field is itself a quadratic field, but it's like crucial to the understanding of cubic stuff because it's the primitive cube roots of unity. I mean, it's probably all sorts of things to say about that, but again, I'm not sure I have anything intelligent to say about it.
Sorry, so what's I was busy writing stuff. So what's the analogous thing here? So what you just said about Eisenstein? Oh wait, or is it though?
It is here, yeah.
Oh,
so,
it is this one, sorry.
So yeah, let me see if I can find. Well, first of all, let me tell you how many subgroups I think this has. So this has, I think, 30 subgroups, which is a little bit annoying comparing to the 8, right? One of the things is we like the other one because 8 is a manageable thing.
Yeah.
So 30 is probably, in some sense, already more than we need. So I guess what I'm saying is that right. So both of these numbers, 7 and 9, they both get the same Euler-Totient, which is 6, but they get it for different reasons, right? 7 gets it because 7 is a prime, and you just subtract 1. But 9 gets it because 9 is a prime power. And so how does it work? The multiplicative group of a prime power, it's like, at the first stage, it's the multiplicative group, but then at the other stages, it's like the additive group. So, right, at the first stage, we're getting this factor of 2, but then at all the other stages after that, we're getting factors of 3. Again, there's probably some much more conceptual way to say that, but it's true, right? I mean,
so the way I'm thinking about it, sorry, it's more primitive. So I start out with Z mod 9. throw out the multiples of 3, and I'm left with 6 things. So it's a 6-element group.
That's right.
And then how do I see that it's Z? Well, let's see. Well, as long as I know it's abelian, then I guess and it has to be Z mod 2 times Z mod 3 because there's no other.
That's true. That's true.
That's a crap.
Right. It doesn't have much choice, but there are some more conceptual reasons why this thing. I mean, I want to say something like, yeah.
Anyway, I liked I didn't know that. So you say that like in general, you get like, you start with the
yes.
You start with the first power of the prime, and then from then on, you just sort of keep semi-producting it with.
No, it's not semi-direct. It's some kind of, you know, abelian extension. And it's, you know, so it's got some sort of carry digit 2 cocycle, and it's a very nice carry digit 2 cocycle. But and there must be much more conceptual ways to say it. But I'm just thinking of it very concretely at the moment. Is there some? I mean,
it makes it sound like I should think of it in terms of actual carry digits, where I write numbers mod 9 is like I write them in base 3.
I think it might be something like that, but I'm just forgetting exactly how it works. What am I trying to say?
I can do multiplication mod 9, where I write my numbers in base 3 using 2 digits, and that already.
Maybe that's all it is.
That already gets carried.
I think that's right. So
that's multiplicative carrying, which is not what you normally talk about when you're telling people about cocycles as carry digits. So this is like the next lesson in carrying digits.
Yes, but it's a good thing to think about.
Yeah.
In terms of in terms of carrying and the relationship to 2 cocycles. So it's like the units digit is special and all the others after it are sort of not special or something like that. Is that right? Is that right?
Yeah, I think it's true. When you're multiplying these 2-digit numbers.
Well, it wasn't the 2-digit.
Well, I'm just doing 2-digit ones.
All right, let's
you
just
never multiply that. You never multiply the higher digits because they would run off. It's being too. So Z mod 9, I think it was like 2-digit numbers in base 3, and when I multiply them, I need to multiply the ones places, and I need to multiply a ones place and a threes place.
Yeah,
but I certainly never need to multiply 2 threes places because that like runs off. That could mean nothing.
Right. Now, I think what was confusing me here is that when you go up to multiple digits, it does really still working, but it's just that the higher digits sort of encrypted or something like that. So you don't really see the but it is, I think it is, I think it is true that the multiplicative group. Yeah. Oh, okay. All I'm saying, I guess, is that for the multiplicative group of Z mod P to the N, there's a short exact sequence. So this group maps down to Z mod. I assume that's right.
Mod P to the N minus 1.
Yeah, I didn't. Okay, I didn't say it right. What we're talking about is we're talking about GL1, comma Z mod P to the N.
Yep.
And that has a short exact sequence where it maps down to GL1, comma Z mod P, which is of size, that's the multiplicative group. So it's of size P minus 1. So that's the quotient group in the short exact sequence. So and then there's the kernel, which is the subgroup. And that kernel is the additive group. And yeah, and there are all sorts of fun things to think about here, but I'm not sure I can say much intelligent about it if I haven't thought about it in a while. But there's there's also fun things to think about here, both at a conceptual level and at a sort of gritty digital computation level, and maybe connecting those two levels. So yeah, somehow that GL1 comma Z mod 3, that being a 2-element group, the multiplicative group of Z mod 3 is 2 elements. That has to do with the fact that, the Eisenstein field is a quadratic extension, but it's very related to cubic extensions. It interacts with cubic extensions in a very interesting way. And that's part of what's going on in this situation here. So you're right. So one of the things I'm saying here is that, there's the horizontal and the vertical dimension in this square. And for the horizontal dimension, corresponding to the number 9, we're very interested in the fact that it has that factor of 2 in it. So we want to keep that. But for the number 7, I really don't care about the factor of 2 for 7, because that's, at least at the moment, I don't care about it. Maybe I should care about it, but I don't care about it, because I'm just interested in the cubic extensions and the single quadratic extension, which gives the Eisenstein integers, and then how these combine with each other and stuff like that. So I guess what I'm saying is that there's a slightly simplified picture, which will cut us down from 30 subgroups to just 12 subgroups, I think, like that. So that's a much more manageable picture to play around with. So what is this? What is this simplification I'm suggesting here? I guess I'm suggesting that we should look at it like this. We're going to have so yeah, on the horizontal dimension here, we're still going to have the general linear group of Z mod 9. But on the vertical dimension, we're going to have a quotient group that gets down to a 3-element group. So you say we'll have an 18-element group, which sort of it still has 2 factors of 3 in it, is good, and it just has 1 factor of 2 in it, and that's just there just because of the Eisenstein integers, which is kind of exactly what we want. So how does this work? We have 3, and I think it's like this. I mean, do you see what I'm saying? I guess what I'm saying, if I think what I'm saying is that as far as subgroups that we might have up here, we want the bottom half of the picture to just be a duplicate of the top half. So let's see, right, there's like that. Am I saying that right? Yeah, so that's a 2-element subgroup. So that corresponds to this. I say that's right, 18-dimensional field. Is that the way this works? Yeah, I think that's right. So, yeah. So, okay, so first, okay, so we're dealing with a group of size 18, and it's this group right here. It's this group right here. So, right, so this is corresponding to this is corresponding to a portion of the 63rd cyclotomic field. It's not quite the whole 63rd cyclotomic field, because if we use the whole thing, then we would get these 30 subgroups, and that's slightly too annoying to organize into a Galois corresponds. So we're just going to take this field that's half that dimension. So if instead of being 36 dimensional field, it's an 18 dimensional field, only has 12 subgroups, and we can survey them in a way that we can sort of picture it fairly nicely. So so first of all, let's just draw the poset of factors of 18, right? So that goes like 18 divided by 3 is 6, divided by 3 is 2, whereas 18 divided by 2 is 9, and then 9 divided by 3 is 3, and 3 divided by 3 is 1. So yeah, this is like the factors of that. And so, you know, by Cauchy's theorem or whatever it's called, all the subgroups are going to be of these sizes. And
Lagrange's theorem? No.
Is that right? Lagrange's theorem?
Sounds more right. I don't think Cauchy
Okay.
messed with subgroups, but anyway, yeah.
Okay, I don't know.
Doesn't matter. I know what I mean. Some French guy.
Okay. So yeah, so I think the way it's going to work out is that there's going to be like one subgroup there, 4 there, 1 there, and 1 there, and 4 there, and 1 there. And if you just look at this little part of the picture, you might recognize that poset as being the poset of all vector subspaces of a 2-dimensional vector space over the 3-element field.
That's the same thing as the subgroups of Z mod 9, or
Yes, not Z mod 9, Z mod 3 squared.
Oh,
If I'm doing it right.
Yep.
That's right. So like this 9-element subgroup. Again, I'm getting really confused about the upside down. I always get confused about the upside downness of the Galois correspondence. So what are we doing? We're having big subgroups. Let's see. Big subgroups at the bottom. Small subgroups at the top, right? Because we're having big fields at the top and small fields at the bottom. So what am I trying to say? Oh,
you mean these bull numbers in black aren't the orders of the subgroups? They're the indexes of the subgroup? You can change your
I think
mind.
that's right. But again, part of the annoyance, I think, is that this picture is actually the same picture upside down. So
right. Yeah.
yeah.
Well, okay. That could be good or bad.
Right. So yeah, so maybe let's see. So let's see. There's a right. So I think this thing right here corresponds to an index 2 subgroup. Is that right? Right. And I think that index 2 subgroup is this thing right here. Which you can see is like, right, it's like a 3x3 thing. Which you can sort of think of as being a vector space over the 3-element field. And right, so the 4 subspaces of this element, right? That's saying like it's the projective line over Z mod over F sub 3. The projective line over the 3-element field. Boy, we have all these, right? We have all these funny interactions between finite fields and number fields, and I'm sure it's not a coincidence, but there's probably a bunch of level slips going on about all these interactions. But so, right, I mean, you can sort of almost see where the 4 vector subspaces are here, or the 4, right? The 4 one-dimensional vectors. There's one right there. There's one right there. There's one right there. And then there's the funny one. What?
Yeah. There's one more. Yeah. The
Yes.
rest of them.
Yeah, those, yeah. And that's somehow the weirdness of that one is just part of the price you pay for thinking about finite fields. I mean, weird things about finite fields. And so okay. Okay, so let me make an attempt to draw this whole thing here, okay? This whole Galois correspondence sort of. So what does it look like? We've got like right, and this may be the time when I really do need to take advantage of the fact that this is sort of an infinitely large virtual piece of paper. So let's see, maybe go a little bit further down here. So what have we got? We got sorry, I'm having some horrible, what's that called? Optical illusion with when you look at a chain link fence, and I'm looking at this grid and my eyes are doing something funny. Or else
Crossing your
maybe,
eyes.
yeah, maybe the machine that is actually, is it my eyes or the machine that are malfunctioning? I'm not quite sure, but I'll try. Let's see, maybe
So what, you're going to draw 12 of these 3 by 6
I think that's right.
rectangles? Oh God, okay. Now, you know, people like Christian is easy to like just copy, draw something on his tablet and then copy it and slide it over.
Yes, I'm sort of supposed to know how to do that, but I'm
Right
not
now I'm wishing you would do that for the first time. So you don't have to draw 12 of these things.
Are they really all going to look the same? I guess you're right that they are going to look the same. All right, let's experiment with this. Okay. And now, but now what do? I click on it or something like that?
Yeah, either it'll move it or it will copy it, depending on. Oh, good.
No,
Oh, God.
how do I how do I copy it? Let's see.
Try right clicking. What does it give you options if you right click on the right of your mouse? No, well, that's just. Well, it is nice to be able to move things, but that's not going to help at all now. I think you're doomed now unless you.
Well, but let me just right. I mean, again, all this would have been great as preparation.
Yep.
Instead of
you don't want to click on the right on your mouse. You don't want to right click. You don't want to. Yeah, there.
Copy. Okay.
See?
Okay. And now, so okay, so what are you telling me?
You right click and click on paste. Yeah, okay. It did actually save time.
Did it really? Maybe you're right.
You'd be busy drawing 12 of these things right now. In the other version of the universe,
Oops.
You're busy drawing 12 of these grids.
Let me turn them on. I clicked it. All right, and then there's one up here, sort of. That's not right. Oh, get rid of that. Get rid of that. All right. That still goes there, I think. Let's see. Let's see. Okay. Let's see. It's doing all sorts of things that I don't like. Let's see. Okay, that goes there. It still goes there, right? A little bit further on. Okay, and I'll try to draw one up here. How do I draw that? Let's see. It was working so great before.
So if you right click, it doesn't give you another paste option?
It's
Oh, what did you do? Okay, you blew it. Oh, yes.
okay, that's about where it should be. And then there's just like a thing that's like above that. It's sort of repeated above that. Is that the way it works? Let's see. Do I have a picture of this in my
Oh, I
face?
see. Yeah, you did. You do. It's that red thing that's just barely visible. Oh, do you have one? I'm not going to draw this in my notebook. I'm going to just watch you.
Right. Oh, okay. So I've got my ridiculous picture here. So what does it look like? It does look like just another one of those. Okay. So I've got it right. Got to draw. Well, so first of all, maybe I should sort of draw in the connecting lines here, right?
Mhm.
Well, or maybe right. Maybe I should first try to. Let's see. Okay,
You
let's
could copy that whole big wad of stuff.
yeah. Let's try that. Let's try that. It's supposed to be really ridiculous. So am I doing this right? Not the right thing. Okay, let's just. Why is it? Why is it doing these things?
It looked okay. You're just not starting at a corner. Oh, a lasso, I see. A lasso.
See, it's giving me this wrong thing here. I don't want this thing. I want this thing. How's it work?
I think if you start wrapping around some stuff, it may get more intelligent. No,
No. It was working before. Let's see. The 10 malfunctioning. Let's see.
Oh, it may be because it already has something in its buffer. Maybe you have to like right click and do something. Like when you said paste, I think you could try right clicking. Yeah, there. No, I thought there was like some option to like to quit, but never mind. Oh, too complicated.
Let's see.
Well, you could probably just paste.
Yeah. Okay. Let's try that. Let's try
more of
that.
those
Let's be ridiculous.
Not try to be too intelligent.
Okay. And then. Yeah, this is terrible. Just thinking stupid wild guesses about how to get this to work each time. Let's see. It's doing the wrong thing. It's doing the wrong thing. Well, that was the right thing, but. Ah. It's up here. All right, all right. Is that about right? Okay, okay, let's try that. And then, so right, it's like, what am I trying to say? It's like, sorry, it's supposed to be like that goes there, that goes there, right? This is all. I mean, I guess this is a very sloppy way of drawing it, but you're getting the idea, right?
Yep.
And so same thing up here. Sorry. I'm doing this right. And then this is all up there. Right, this is ridiculously sloppy, but okay, and then
You don't need to draw the vertical lines, I don't think. I mean, if you could.
but that is what they all are. That's
They're all-
the way it works. I mean, this
That's
gives
like,
us
yeah.
this
Okay.
gives us a pretty much complete.
Yeah. Okay, that's okay. Yeah, not too bad. Yeah.
So okay. So right, one of the things that's sort of misleading about this picture is that it sort of misstates that, right? The heights corresponding to the different dimensions, right? I mean, so like this is like the one-dimensional stuff. This is the cubic extensions. There are these 4 cubic extensions corresponding to the 4 points of the projective line over F3. This is actually a quadratic extension, so I should have shifted it somehow, made the 2 lower than the 3.
Uh-huh.
And so this is 1, 3, this is 9, right? This is 2, 6, and 18. And okay, so what do they look like? So there's like, this is the whole thing. This is just so right. This is where the Eisenstein integer, the Eisenstein field is. This is where the Eisenstein field is.
Huh?
Right?
Guess so.
And we know that that is like, not a purely real field, right? That's I can't remember the right terminology for it. Maybe it's like a totally imaginary field or something like that. But it's very complex rather than real. And so that means that, this step here is very much ramified over the infinite prime. How do I know that? I don't know. We've talked about that before. If we really understood this, then that would be an obvious thing to understand.
Uh-huh.
But I think that means that all these other steps are ramified over the infinite prime as well. I mean, this is a little bit strange, but it seems like these should all be real fields beneath. And then, you know, when you
Is that
go
really how it
up,
works? I mean, you're claiming that like,
well, we've talked about that before, right? That you know, you get one chance to pass from real things to complex things.
right, but now you're
Every path
saying
has
there's
to
like
has to-
more,
Yeah.
now you're sort of saying that like all those one chances happen in analogous positions.
In this example, they do. Well, I mean, when we do the example for the 20th cyclotomic field, it didn't look like that, but I think that might have been because we didn't try to draw the picture in that way. There may have been a more systematic way to draw the picture where you would have seen that picture that you can.
Yeah, that didn't occur to me at the time.
Yeah, so that might have been a bad feature of that traditional picture that I draw. I don't know which, you know, they may have different pictures have different advantages and different disadvantages. And I'm not sure this is right, but that's what I think must be going on here, that these must all be real fields, these must all be complex fields. Which sounds like it's going to be, if that's really correct, then that should be important in understanding these Z mod 3 torsors. It's funny that they're all.
Well, I don't know if
real.
I don't know why you are so sure they are, but
Why do I think that they're all real?
Yeah, I mean, if you tell me what they are, we'll see. But,
I don't know yet. You know, you caught me right in the middle of not really knowing exactly what they are yet.
you can probably guess what some of them.
Yes, I think there's one of these four. I do know what it is.
But don't.
Yeah.
But when you do it, can you?
Actually, is that
When you
right?
do a cubic extension, are you allowed to just put in the real cube root of your number, not the other ones? Don't you like have to put in the
That's a good question, and it's the same kind of question I've been asking myself. I think after we understand things, we'll see that it's not quite like that. But that's part of what we're trying to understand, right? We're coming with crazy things like what you just said, which probably don't make sense. Maybe they do make sense, but I still think
I thought that like if you stuck in like a cube root of. Can you tell me like what one of them should be? So it should be like a cube root of what? Of
one of them is going to be a cube root of the cube root of one, the cube root of one. One of them is going to be, one of them is going to be the cube root of a primitive cube root of one. Let me see if I can figure out which one that is. So that would be, don't tell me, let me think about that. I'm supposed to know this. Actually,
that's a cubic extension. I thought that should be like I thought that has size 9.
Yeah,
that's a 9-dimensional.
Right. Okay, right. I didn't really say that. So these doppelgangers up here that are actually more like what I'm saying. So what am I trying to say? So there's like, okay, there's this thing here. Yeah, so I think there's, am I saying this right? There's this one here. Right. So this one is the Eisenstein field. And then this one is where you take the Eisenstein field, which has a primitive cube root of 1 in it, but then you give that primitive cube root of 1, you give it a cube root as well. And that's this thing right here. But that creates this mystery about what in the world is this thing here? Because you see what I'm saying? It fits in with those, but it's apparently real. But this, okay, I have some vague ideas what it is, and it's based on this, fumbling around with this Tanakian viewpoint. And I think it's going to be something like, I'm not sure this is correct yet. And there should be some very highbrow ways of thinking about it, which should be very beautiful, but there's also be some very interesting lowbrow ways of thinking about it. But I'm not sure I've got any of these ways correct yet. But I want to take a guess that it's something like, yeah, my lowbrow guess, I'm not sure it really makes sense yet, but it's going to be something like, what am I trying to say? That well, okay, so one thing it may be is it may be the real part of this field. That may be one way to, and that's a Weasley way of defining a field, but it may actually be correct. And you know, we've used that Weasley method of defining a field before. It's right. It's Weasley because it doesn't give you a very explicit account of what are the numbers that are generating this field.
Yeah.
There are all the real quantities in there. But I think what I was going to say was I was going to suggest that.
Okay, well, that's okay. So I mean, in fact, then you're making me think that we should define the 4 in that horizontal row on top and just define the other 4 to be the
That's
real
right.
part.
That's right. So right, we're actually mainly interested in these 3-dimensional ones, but these 6-dimensional ones that are related to them are actually seem easier to understand because they, well, it depends on your viewpoint, but in some ways the 6-dimensional ones are easier to understand because they are extensions of the Eisenstein field. And so they're cubic extensions of the Eisenstein field, which means that I think it means that they just sort of obey the classical rules of cubic reciprocity, which means I think, you know, it's just attaching a cube root of something to the Eisenstein integers. And right, when you attach one cube root of something to the Eisenstein integers, you attach all 3 cube roots of it.
Right. Okay.
Yeah, so you're getting this abelian cubic extension when you do that, and that's sort of the way classical cubic reciprocity works. But like I say, there are highbrow ways and lowbrow ways. I think you know, like we said, one way was to say maybe it's the real part of this 6th degree thing, but another way to say it is, and I'm not sure this is correct, but let's try. I want to say something like it's the field of the real coefficients of these numbers up here, right? I mean, this is, you see what I'm saying? The numbers up here should have coefficients what am I trying to say? They should have like a real and an imaginary coefficient, but in some sense, I mean, you
mean you just think of them as sitting in the complex numbers in a standard way, and you just take the real and imaginary parts.
Except that it's not quite, that would make it sound like we were dealing with, you know, 1 and I, but it's not 1 and I, it's 1 and the primitive cube root of 1.
Oh, okay.
So it's something like that. I'm not even sure this is the correct way to think of it, but it may be something like that. But right, it's supposed to be like it's supposed to be like the. I mean, if this is all correct, then that should agree with the way of thinking where you say that it's the real part of the field. But let me try to say a little bit about the more highbrow way of thinking about it. So the more highbrow way of thinking about it is the way that really connects with the Tanakian viewpoint. It's supposed to connect with the Tanakian viewpoint. And it's supposed to say something like, what am I trying to say? Right, remember that this Z mod 3, it doesn't have, over Q, it doesn't split. It doesn't have these 3 one-dimensional representations. It has a trivial representation and a 2-dimensional representation. And that 2-dimensional representation, it's an irrep, but it's got a commutative division algebra, which is basically the Eisenstein field. I mean, it's endomorph, right? The endomorphisms of this, right? That's probably something you've taught me about, right? That the endomorphism algebra of an irreducible, in a certain context, endomorphism algebra of an irreducible object, probably some theorem or lemma or something that says that that is a division algebra or something like that. And here, for some reason, it's a commutative division algebra because we're dealing with a real abelian stuff or something like that. And in fact, it's the Eisenstein. So I think, right. See, what I want to say is something like that, right? We had a Z mod 2 torsor is really secretly the same thing as a line object equipped with a trivialization of its tensor square. Now we're trying to do similar kinds of things for Z mod 3 torsors. If we're already doing it over the Eisenstein field, then we probably all we have to say is that it's a line object equipped with a trivialization of its third tensor power. But that's taking advantage of the way, you know, it's splitting. The group is splitting over the Eisenstein field. But if we're doing over this field that it doesn't split over, I have conjectures, and it's going to be something like this. It's going to say it's the theory of an Eisenstein line object. I mean, I think we already talked about this last time, but again, I didn't really understand it last time either, and still don't have it. It's going to be the theory of an Eisenstein line object with a trivialization of its third tensor power, but then also with some other extra structure or something like that. And
sorry, that's supposed to be the full description of a Z mod 3 torsor over Q.
yes, and it's sort of still very incomplete so far, but it's going to be very nice when we figure it out. But
so when you say an Eisenstein line object, that's supposed to like get you, if you just said that, that would like get you the guys on top, but not the ones down below or something.
Yes. So this, right. So it's like we're saying, you know, and then we're gonna have those gauge fixing tricks, right? Where you think of it as like a twisted group algebra or something like that, at least in one picture or something like that, or something like that. And what am I trying to say? That what am I trying to say here? Well, okay, so right, we worked out this idea that when you have the gauge fixing trick, when you apply it to the case of a line object with a trivialization of its tensor square, we thought about that, and it worked out to just kind of saying that the Z mod 2 torsors are classified by the square free elements or something like that, the multiplicative group or something like that. And because it's a gauge fixing thing, right? That means it's a sort of lowbrow thing. So, and you know, it's right. It's sort of lowbrow in a way that I don't know how well I can trust it to generalize perfectly. But nevertheless, let's pretend that we can figure out how to do that. So what am I trying to say? That now we're trying to do this for the Z mod 3 that doesn't split. So I want to say something like, see, I still think we're going to be taking a cube root, but it's not, it's going to be a cube root of a formal Eisenstein number. So I think that these three-dimensional things are going to be generated by the coefficients of a formal cube root of some Eisenstein number, some formal Eisenstein number, sort of a formal cube root of a formal Eisenstein number. Do you have a sense of what I mean by formal in this context? I mean, right?
Not completely. It sounds like you're wanting to not talk about the actual Eisenstein numbers, which sounds like you could if you wanted to.
Well, there's probably going to be equivalent pictures where you can, if you think of it in the formal picture, it's probably going to be equivalent to some actual picture or something like that. But
right,
so, yeah.
In some doctrine where you're working over the rationals, you can set up, I'm not quite sure what I mean, but you can set up things that act like Eisenstein numbers. I'm
yes. Yes. I mean, right, a formal Eisenstein number is just a pair of ordinary numbers.
Yeah.
And, you know, normally the thing that makes it formal is that this works not just when the single components are ordinary rational numbers, but the single components could be taken from any field. And, you know, so a formal Eisenstein number working over any base is, you know, two components from that base. And one of them is the component of the constant component. The other one is the coefficient of the favorite primitive third root of unity. So right. So, you know, I'm trying to apply this very conceptual viewpoint, but I haven't succeeded yet. So it could be that all the things I'm saying here, this whole little Galois correspondence here, this could be something that, you know, various other people already know or exactly what all these are. And I don't know yet exactly what all these are, but it's very fun trying to figure it out and using all sorts of different approaches trying to figure it out. And like I say, I mean, there's this one over here that I'm pretty sure I know exactly what it is. That it's the right. You can also say that this is the ninth cyclotomic field. This is the ninth cyclotomic field. This is the third cyclotomic field. This is the 1th cyclotomic field. Third cyclotomic field, ninth cyclotomic field. Now, where's the 7th cyclotomic field? Oh, well, we don't have the full 7th cyclotomic field, but I guess this would be the real part of the 7th cyclotomic field. I think that's right. Is that right? I think that might be right. I'm not sure. Okay. Let's try going back a little bit here. Do I have enough to? Yeah. Okay. Wait a minute. Let me see if I can. All right. I want to see if I can erase some stuff here because can I erase those question marks? Okay, and then try to draw back in that vertical line there. I guess goes there. Or something. So okay, let's say if we can put what some of these are here. So let's see, we have. So what is this index 3, 1 right here supposed to be? That's in. Oh, so it must be. You're trying. I guess you're telling me it should be like this. Like that, right? Let's draw this. Right, the Galois correspondence of the 6-dimensional one seem easier to draw. So it's like, right, this one that goes. How does this work? Is it something like? Sorry. Like that? And yeah, I guess it's like that. And then there's one like this. And then there's the weird one, which looks like what? It should look like this.
Yep, like movie things, yeah.
Okay. And now what do these ones look like? These ones look like this, and this, and this, but then there's also sort of staggered this and this. And it must be there. I think it must be like that. And then this one must be.
Oh, that's all the way across. Just all the. Yep.
All right. I have a feeling that this one maybe should have been drawn at the end or something like that. I mean, you know, I don't know about what's the order to list these in or something like that. And this one is what? This one, and this one, and this one, and then this one, and this one, and that.
That's nice.
And there may be better ways to arrange this, better ways to identify what all these fields are. And what, okay, so what are these? This one is just that one. And this one is this one and that one. Does that all look correct now?
Yep.
That looks correct. All right, okay. So like I say, this is
Just those ones that only have the red dots in the top row of your box.
yes.
Those somehow like only care about Z mod 9. Wait, no, yes.
I think it's Z mod 7, I think, or something like that. Yeah, yeah. So the,
Oh,
the very
yeah.
vertical ones, let's see, is that right?
Your horizontal axis had there's always this backwardsness.
Yes, yes, in 2 dimensions, you're right. The x-axis is where what? Y is
0, but
0. Okay.
your horizontal axis was labeled by elements of Z mod 9 back when you were drawing the
That's
chart.
correct. That's correct. That's correct.
And I just think we could understand those 3 particular extensions more easily than the rest.
I mean, now you got me worried that I got them backwards or something like that. What am I trying to say?
I think that they're related to Z mod 9, that there's like one of them is, yeah, I see, maybe it didn't get them back. But there's sort of an obvious thing to think about, which is like, well, no.
Yeah, I think those are the ones that relate to Z mod 7.
Okay, so what should they be? Let's see, what are they as?
Let's see. It should be,
So something you're throwing in a primitive 7th root of unity. Right.
oh, okay, yes. Well, okay, right. There are ways we can do things like that. Right, right. So, okay, right, okay. Yeah, you're bringing up a very good point here, which is, right, there are some very interesting contrasting ways to study all of this. What am I trying to say here? That there are ways that you can study this whole business by looking at the whole thing as a bunch of little torsors relating to each other, and part of our plan is to really approach it that way. To, you know, it's like, so there's all these Z mod 2 torsors and Z mod 3 torsors. There's a whole bunch of them, and you know, each one of them is very small. It's like a Z mod 2 size or Z mod 3 size, and part of the goal is just to understand in general how an arbitrary Z mod 2 torsor works, how an arbitrary Z mod 3 torsor works, and, you know, more generally how an arbitrary Z mod n torsor works for any n. And that's a good approach, and it's probably really related to, we're probably trying to reinvent art and reciprocity or something like that.
Mm-hmm.
But there are other approaches. So, for example, there's another approach where instead of looking at all these little tiny torsors, you try to make the whole thing into one big torsor. One big torsor of one big abelian group of one big abelian, one big torsor of one big abelian group. And that's sort of like the universal torsor, universal abelian torsor for over the rational field, for example, like that. So in other words, it's a torsor of the universal abelian Galois group of the rationals. Which is basically something like, I want to say it's something like, I don't know, I'm always afraid I'll get the details slightly wrong or something like that, but it's something like some sort of profinite completion of the, what do I want to say? I mean, it's like an inverse limit of
cyclic groups.
multiplicative groups, an inverse limit of GL1.
Right. Yeah. Yeah. Yeah, it's a famous group. Yeah. But I was getting the wrong famous group, but yeah.
Yeah, I mean, I hope I'm not saying it. There's room for me to making little tiny mistakes in there, but the basic idea that this is an inverse limit of GL1s for over all these quotients of Z is roughly correct. And right, in some sense, to understand that one big universal abelian torsor over the rationals, all you have to do is understand cyclotomic. And later, this idea generalizes to, like, when you're working like the universal abelian torsor over the Gaussian field, or the universal abelian torsor over the Eisenstein field. And that's kind of where Kroneker's Jugendraum comes in. And so, it's sort of like, to understand the universal abelian torsor over the Gaussian field, you just have to understand the, instead of the cyclotomy, which is kind of the torsion on the multiplicative group, this is the torsion on the Gaussian elliptic curve. And similarly for the Eisenstein elliptic curve. And so these, I'm saying, so these Jugendraum things are sort of focused on giving you a unified picture of this one big torsor, this one single universal torsor of this big abelian group, of this universal abelian Galois group. Whereas, there are these other approaches where we sort of just try to understand what the arbitrary, the general torsors look like for, these nice small abelian groups like Z mod N. And then we want to figure out how all these pictures fit together. And it kind of fits together in a way that, because of all these Z mod N's inside of the GL1s. So, right, you have to understand, like, for example, right, inside of this, one of the things we're saying is that inside of this GL1 comma Z mod 7, there's like a little 3-element group and a little 2-element group, a little 3-element cyclic group and a little 2-element cyclic group. And that's telling us about little Z mod 3 torsors and little Z mod 2 torsors that are sort of part of this big, relatively big GL1 comma Z mod 7 torsor. And that's just a little part or copart or whatever of this bigger inverse limit. Right, and I am probably getting parts and coparts mixed up because of all the Fourier duality and Galois upside downness and everything going on here. But I'm not going to worry about that too much right now. It's very important to get that straight. But so like I say, there are different approaches to learning all this stuff, and when learning it, it's permissible to, use both methods at the same time and learn about one method by using something that you sort of halfway know from the other method, even if you don't completely understand all the details. So I think I'm suggesting that one of the things you were suggesting a moment ago that really reminded me of what we should be, some of the stuff we should be doing, is that we can really use this sort of universal guide. We can use this one big torsor as a guide in understanding all these little torsors. It's like we're going to sort of think of all these little torsors as little parts of this big torsor. And the big torsor we're going to understand in some ways because we do understand, you know, these GL1 comma Z mod n for an arbitrary number n, which in particular is probably not a prime, you know, because the whole inverse limit is, you know, getting away from the primes, getting to more and more composite things. And so right, okay. So, but what I'm really trying to say in concrete terms is that all the quantities that we're trying to understand here, one way to understand them, which I was kind of shying away from until you just reminded me that we can do it, is we can simply obtain generating quantities for these fields just by taking the appropriate primitive roots of unity and then, you know, symmetrizing them with respect to the appropriate Galois group. So yeah, so what am I trying to say? So like, you have some examples here. Yes, okay, right. So this one right here, we do know, we have one particular, we have, right? I think we should have one particular description. Boy, is this going to work? I guess this is promising that it does seem to. So, right, if you think about what this one is saying, I think what we're saying is, right, yeah, and again, right, this one is really, you can completely ignore the Z mod 7 and just think about the Z mod 9 in this one. And what it is saying is that it should be generated by 1 to the 1/9 plus 1 to the 8/9. And notice, I didn't even realize this before, but notice that that really is a real number. Isn't it?
I thought that's what you, so how did you attain that? I attained it by taking the real part of 1 to the 1/9 and multiplying by 2. Where did you get the 1 and the 8 from?
Okay, let me see if I can figure it out, because it's, I have a great answer for that. I have a great answer for that because, you know, it's like, remember what it was. Remember how the labeling works. It's 1, 2, 4, 8. So it's the 1 and the 8. It's right there. So, you know, with this one over here, we can't just use the 9th root of unity. For this one over here, I think we'd have to use the actual 63rd roots of unity, and we'd have to add 1, 2, 3, 4. We'd have to add 6 of them together. And then with 6 to add together, this is where we would need that Chinese remainder data, which should come in handy.
Right.
But
you could do the,
we might actually need 12. Is that right? Because I mean, right, I cut off this. This was really originally a 6 by 6 square, and I was economizing by cheating and thinking of it as a 3 by 6 oblong. What were you going to say?
I was gonna say,
Yeah.
I was wanting to know what the one on the very right hand,
Here?
not that one there, is.
Which one? Where?
That's sort of
Here? No.
No, the one you were just pointing at.
Oh, this one here.
The very right hand, that one, the circle one, yeah.
Okay.
That seems like that one should be one of the ones that is sort of simple. to figure out. I'm
I guess you're right.
a little
Uh,
confused. Because it seems to have a lot to do with that 1 and that 8 that you were just talking about, but it's doing something different with them.
Well, like I said, you still have to work out the Chinese remainder theorem. So remember where it was, right? This was like, if I remember correctly, this was like 1 and 6 were right there, and then 3 and 4, and then 2 and 5 or something like that. So this is like folded up or something like that. Maybe folded isn't quite the right word, but so I think it's actually gonna be 4 things added together. And it's gonna be, whatever these 4 numbers are, it's 1 to the, that number over 63 plus 1 to that other number over 63.
Yeah.
Plus, 1 to that other number over 63. And 1 to that 4th number over 63. So you can get these very explicit descriptions of the quantities that generate all of these fields just by taking appropriately invariantized sums of 63rd roots of unity, or in general roots of unity, whatever these roots of unity are. And so that's a complete answer, but it's not a completely satisfying answer to me. I mean, that's one very important answer. I mean, how does that answer work? It works by we're sort of exploiting the Kronecker-Weber theorem, which is sort of like the baby case of Kronecker's Jugendtraum. It's the case that works on the rational field instead of the Gaussian field or the Eisenstein field or something like that. Because cyclotomy, as I say, is just the torsion on the multiplicative group. I mean, this is going to be a help in figuring things out, right? I mean, these are very explicit answers, but they're dissatisfying answers, unsatisfying answers in certain ways, because right? I want these. I mean, all the answers are satisfying and dissatisfying in complementary ways. So, maybe this is a good answer, but there are other ways of thinking about it. Like I say, I really want to understand this other way that says that this field is generated by some Eisenstein formal cube root, which we want to understand. So let's see. Let me think where we are. Let me think how much time we have left. And I mean, I have a feeling I sort of feeling I have the feeling that I'm doing a reasonable job today of sketching out all this raw computational material, this raw concrete example, raw store of concrete, a store of raw concrete examples that should be good raw material to use for understanding the more conceptual ways of thinking about this. But I'm perhaps not doing a great job today of explaining any of these conceptual stories, but I think you're getting some ideas of how it works. I mean, but right, we really, really want to return to and really learn the Tanakian way of analyzing all of this. And again, right, the Tanakian viewpoint, it embraces both the viewpoint where you think of one big torsor, like a torsor of this inverse limit of GL1s, but it also embraces this other way where you think of it as, you analyze it, big torsor into these little torsors that are, you know, like Z mod 2 torsors and Z mod 3 torsors and Z mod n torsors, et cetera, et cetera. So let's see. I have a feeling I was going to say something else, but I forget what it was. Let's see. So I guess you're telling me that when you're writing these as these invariantized sums, it does get sort of easier towards the top of the diagram, because you're doing less invariantizing, less symmetrizing. You know, like at the very top, you just take that 63rd root of unity itself. Is that right? Yeah, primitive 63rd root of unity. All right. Let's see.
Yeah, it sort of does its own invariantizing, because if you pick a particular 63rd root of unity, then different powers of it, certain powers of it will give you all the other primitive 63rd roots of unity. So you don't have to, well, I don't know. So it gets to be invariant under the group that's permuting those. The field that it generates is invariant under the
okay, that sounds like a really big level slip there about the field being invariant versus a particular quantity being invariant.
Yeah, well, yeah, that's right. Well, true. Yeah, okay, never mind. Yeah, yeah, it's true.
Right, I have a feeling we had a big fight about that one time. But let's see. Well, right, okay. So okay, it's maybe I should sort of try to wrap it up right now. But what am I trying to say? I mean, unless we have anything else you want to say. But I'm just trying to come up with a punchline here, which again, I'm not sure I have any good punchlines right at this point. But I want to say something like that. Oh well, okay. I did just remember one of the minor points that I wanted to make, which is, so I've been saying that in this Galois correspondence, we have 12 fields, 12 subfields. And we understand why this big field has 12 subfields. We sort of understand. But and it does, right? It has sort of to do with the Grassmannians of a two-dimensional vector space over Z mod 3. Or I guess at least half of it has to do with that. But right, that those Grassmannians, what am I trying to say? Those, or I mean, it's like right. So this is like this is like the one-dimensional Grassmannian, which is like the projective line or something like that. And this is like a zero-dimensional Grassmannian and a two-dimensional Grassmannian or something. Grassmannian of two-dimensional subspaces. But what am I trying to say? That when you're thinking from the torsor viewpoint, instead of looking at the subspaces of this vector space over the 3-element field, it's more like we're looking at linear operators into it, right? So right, there's only these 4 3-dimensional subfields, and there's only these 4 6-dimensional subfields. But corresponding to these 4 3-dimensional subfields, there's actually 8 torsors, right? And that's just like saying, right, that a 2-dimensional vector space over F sub 3, it has 4 one-dimensional subspaces, but each one of those one-dimensional subspaces contains two non-zero vectors. And that's sort of because the multiplicative group of F sub 3 is size 2. So do you see what I'm saying? So like there are two different, there should be two different Z mod 3 torsors corresponding to this field, two different ones for this one, two different ones for this one, and two different ones for this one. And it's like sort of like the difference between projective geometry and linear geometry. Right? Yeah.
I'm confused.
Well, right. So I mean, right, these torsors, right? If right, again, let's fix our group to be Z mod 3. And let's fix our field to be, for example, the rationals. And let's consider the collection of all Z mod 3 torsors over the rationals. And that should form some sort of like cohomology group or something like that. Except, of course, that especially you, and maybe especially you and me, probably want to think of that as like, we want to probably slightly categorify that and think of this as a 2 group or something like that, an abelian 2 group of these torsors. And right, so if you think about how that works, thinking of think about how you add torsors and stuff together in a cohomology group or in a 2 group. Right, it's not going to make sense if you're just thinking of them as like these subspaces of the vector space, right? There's no good addition operation on subspaces of the vector space. So, right, okay, so, right, did you see what I'm saying? Right, let me try and get this right. Let me try and get this right. I want to say something like that. Just working out backwards. I want to say something like that. No, I think it does work. Yes, that, right, yes, I think this is going to make sense. Believe it or not, I think this is going to make sense. In the Galois correspondence, we have subfields correspond contravariantly upside down to subgroups, right?
Yep.
But if you try to think of that from a torsor viewpoint, then we're kind of saying that the torsors correspond not to subgroups, but they correspond to subgroups with their quotient group labeled. Right. So do you see what I'm saying? So like, right, these 3-dimensional things correspond to these index 3 subgroups. So for each of these index 3 subgroups, the quotient group, the co-kernel of the subgroup is a 3-dimensional cyclic abelian group, which can be identified with Z mod 3, but in 2 different ways. So that's how we're getting 2 different Z mod 3 torsors. Right? So, right, it wouldn't make sense to take these 2 subgroups and add them together, but if you think of them as, think of it with the cosets, the 3 cosets being labeled, being labeled, having a specific isomorphism to Z mod 3. Then, by means of that labeling, it makes sense to add these together. Isn't this making sense? I really hope this is going to make sense. Yeah.
I'm probably just not getting it. So there are twice as many of something as something else. There are only
I mean, right.
4 subfields. Is that right? There are only 4 subfields that we're talking about right now, this second, and they're like twice as many.
Yes.
Something else.
Yes. There are only 4 of these cubic fields. cubic subfields. There are only 4 of these cubic subfields of this 18-dimensional field.
But are you saying that there are like 8 of them if you do what? You take the subfield and I'm going to think of it in terms of the subfield. They're like subfields with some extra
Yes.
labeling.
Yes. How does that work? I mean, it's like, what am I trying to say? So, I mean, right, I mean, these.
Is this like you can just take the Eisenstein numbers and you can think of them with in 2 ways, depending on which primitive cube root of unity you take to be the generator? Is that the same kind of doubleness?
I think that's probably that's a little bit confusing to me, but maybe it shouldn't be confusing. That sounds like it probably is the same thing. But I was going to say, you know, what am I trying to say? Like, I mean, right? Think of the homotopy theory picture. So you've got this space, right? And it has some fundamental group. And either you assume that that fundamental group happens to be abelian, or you can just abelianize that fundamental group. And then consider, you know, the abelian covers of that topological space. And right, so there's at least 2 different things that you could do, which is you could take, you know, whichever cohomology group it is of that space with coefficients in Z mod 3 that classifies the Z mod 3 torsors over that space. Or else you could just take the is that right? So let's see, bundles of 3 elements.
Are you talking about like bundles of 3-element sets versus bundles of cyclically ordered 3-element sets?
I think it is. I think that is.
So there are like 2 ways to cyclically order a 3-element set that's compatible with it's preserved by the Z mod 3 action on this.
Yeah, and right, and you can sort of right. You can tensor. It's called some kind of tensoring or something. Right. I mean, right. It's a stabilization phenomenon with the structure group being abelian that you can.
The fact that you get an abelian group of these things.
Yeah, I think that's right. So okay, well, okay. I was hoping that this would be clearer, but I think we're getting some idea of how this works. And
I don't get why you even brought up the doubled thing.
Well, partially it was just for fun. I mean, like you know, there's this way in which, you know, I see the Grassmannians of these vector spaces over the finite fields. I see them showing up. But then I realized that, you know, it's not just the Grassmannians, and not just these. It's not just these unlabeled subspaces of the vector spaces that are showing up. It's these labeled subspaces, or possibly co-labeled, but it's hard to tell because, you know.
How are they showing up unless you deliberately go out of your way to look for them? You made it. I mean,
they're showing up when you think in terms of torsors. When you think in terms of the torsors, these abelian torsors, instead of thinking in terms of these extensions. So, right, I think it is what you're saying, right? If you have these cubic extensions, that is exact. I'm sorry, cubic extensions. What am I trying to say? Okay, I guess what it is, yeah, I guess it is kind of is what you're saying and what we're saying, that if you have a bundle of cyclically ordered 3-element sets, then you could forget that they're cyclically ordered and take the underlying bundle of just plain 3-element sets on there.
Mhm.
And having forgotten that cyclic ordering, you sort of lose the ability to tensor things together. But on the other hand, right, you didn't, there's something that you didn't forget property-wise, which was, you know, that these things, these torsors had the property that they could be given a cyclic order, where some don't even have that. Some can't be given a cyclic order because, you know, there's some holonomy that drags you around and screws it up or something like that.
Yep.
Or maybe I should have said monodromy. I never understand what the difference is between monodromy and holonomy. So yeah, right.
Uh-huh.
These torsors, they give you these cubic extensions of the rational numbers, which happen to have the property of being abelian extensions.
Mhm.
But there are other cubic extensions. Am I saying this right? Is that right? There are other cubic extensions of the rationals that are not Galois extensions. Is that right? Not. Right? Is that right?
Galois, when you make them be Galois extensions, they have Galois group S3. Is that what you mean? They have like,
Well, I mean, I'm trying to say that, you know, Galois extensions correspond to like normal subgroups or something like that.
Mhm.
The Galois correspondence. Well, okay, I'm being very sloppy here. And we're running out of time. Actually, right, maybe I do want to try to say one other thing here. I mean, like I say, I'm struggling to find good conceptual ways to identify all these fields. And we already mentioned one way you could do it just in terms of invariantizing these roots of unity. You know, invariantizes symmetrized sums of roots of unity. And that's one way to get it, but that's not the only way to do it, and it's not the best way to do it. Or there are other ways that I really want to understand. But you know, there's all this raw material. One of the things that I've been doing with these examples, trying to experiment with them, and the experiments are very inconclusive so far. And these are experiments with mathematics and stuff like that, and sometimes just with, you know, struggling by hand. But the experiments are supposed to see these, right? These subgroups are Galois groups, but have this other interpretation in terms of the splitting patterns that correspond to the number fields, right? And we're trying to unify all that together. We're trying to unify the interpretation of these red dots as Galois correspondent subgroups. We're trying to unify that with the interpretation in terms of the splitting patterns for these number fields. You know, that right there are these reciprocity laws that the congruence
Mhm.
Reciprocity law is stating that these abelian extensions split over certain primes that are defined by a congruence condition.
Mhm.
And there's some mysterious and or semi-mysterious relationship between the interpretation of these red dots as telling us about those congruence splitting patterns
Mhm.
versus the interpretation of these red dots as the Galois correspondence subgroup. I mean, yeah, I'm not saying any of this very well yet, but this is all stuff, these are all dreams that I want to get to make very good conceptual sense. And again, I think the royal road that I'm attempting to use to get this all to work is the Tanakian viewpoint towards these torsors over these number fields. But you know, in struggling to get this royal road to work, I'm getting my hands really dirty and gritty with all this
Someone
other
has to
stuff.
build the royal road before the
Yeah.
king can.
Yeah.
It doesn't
Now
feel
you
very
got me this mental
royal
picture.
yet.
Right, you got this mental picture of the, you know, the train that's on the tracks but they're also building the tracks at the same time.
Desperately trying to keep up with the train.
Anyway,
Yes. Okay, we're at the bleeding edge of the royal road.
right. But I hope you're getting some idea of what I'm trying to do here.
Yep, I think so. Yeah.
Okay. Okay, so we'll quit for today, but I'm hoping that you know, we're going to get much more conceptual in the future. Okay, thanks a lot.
Okay, sounds good.
Okay, bye.
Yep.